This is the third part of my lecture on parametric tests for comparing means, and I'm going to look at how to compare a sample with a known population. In order to test a sample against a population with a known standard deviation, what we're given is the population with a known mean and a known standard deviation, and the data we have available are not just a single measurement like in the last example, but a sample of several measurements. What we want to test is whether this sample could have come from this population, and the statistical test that we're going to use is the one sample Z test. The one sample Z test assumes that we have a population with a mean MP and a standard deviation SP, as shown by the yellow population in the diagram. And instead of just having one measurement, we have a sample of n measurements which have a mean MS, as shown by the purple distribution in the diagram. The null hypothesis is that this sample came from this population, and the test statistic is also U, like the last test, but this time is defined as MS minus MP, the difference between the sample mean and the population mean, divided by SEM, which stands for standard error of the mean, and the standard error of the mean is defined as the population standard deviation divided by the square root of the number of measurements. So let's see what that means. The standard error of the mean, SEM, is the precision of the measurement, MS, how accurately we have determined the mean. Remember, we talked about standard error of the mean when we were talking about sampling in a previous lecture, and we know that we can calculate it by taking the population standard deviation SP and dividing by the square root of the number of measurements. The more measurements we get, the smaller the standard error of the mean becomes, because we get a greater and greater precision. The test statistic U is the difference between the sample mean and the population mean as a fraction of this standard error of the mean. And that makes sense because it tells us how far away the population and the sample mean are from each other compared with our estimate of the precision with which we can measure the sample mean. So if the null hypothesis is true, then this test statistic U should follow a standardized normal distribution. So we can determine the probability of any value of U using the normal distribution. Note that if n equals 1, then this becomes the same as a single measurement test, because square root of 1 is 1, so the SEM becomes equal to the population standard deviation, and U becomes exactly the same as the U for the normal distribution test, which is what we would hope, because if our sample reduces to one measurement, it becomes the same as the normal distribution test, which we discussed in the last part of this lecture. So the recipe for performing the Z test is calculate the mean of the sample measurements, then take the difference between the sample mean and the known population mean, and then we have to calculate the standard error of the mean from the known population standard deviation, using the fact that the standard error of the mean is the population standard deviation divided by the square root of n, where n is the number of measurements. Then we divide that difference by the standard error, which gives us the test statistic, which we've called U. And once again, we can look up the critical value of U from the table of the standardized normal distribution. And if it's greater than the critical value, then we can reject the null hypothesis. So let's take an example. What about the intelligence of lecturers? The question which we pose is, do university lecturers have above average intelligence? Well, the experimental hypothesis might be that lecturers have a higher IQ than the average population. So what is the null hypothesis going to be? Well, clearly it has to be that lecturers have the same IQ as the average population. So is this going to be a one-tailed or a two-tailed test? It has to be a one-tailed test, because we're only postulating that lecturers have a higher IQ than average, not that they have different IQ which could be lower or higher. We're only interested if lecturers are of a higher than average IQ. So we need to collect some data for this. Let's get some lecturers to take an intelligence test. So here we see some supposedly intelligent lecturers busily taking a written IQ test. So let's look at the results of the data that we have. We know that by definition the average population has an IQ with a mean of 100, that is how IQ is defined, and a standard deviation of 16. That also comes from the definition of how the IQ is defined, that it has a standard deviation of 16, about a mean of 100. And our 4 lecturers who've taken an IQ test, we find that they have IQs of 110, 104, 114 and 120. I should point out that this is hypothetical data for illustration only and is not intended to illustrate the real IQ of the people shown in the video. So what statistical test are we going to use? Well, the data are quantitative. We have some numbers for IQ. We can assume the population is normally distributed because that is pretty well how IQ is defined, and we also know the population standard deviation 16. That's part of the definition of IQ. So we have everything that we need to use the one sample Z test. So let's have a look at the data first of all. Here we have a scale of IQ on the vertical axis and the error bar with a length representing the standard deviation and a bar in the middle representing the mean shows the IQ for the general population as a mean plus or minus a standard deviation. And the 4 dots show the IQ of our 4 lecturers. So does it look to you like the lecturers have a higher IQ than the general population? They're certainly all above 100, but is it sufficiently far above to be significant? Well, that's what we're going to test. So first of all, to do the calculation, we work out the average IQ. We've got values of 110, 104, 114 and 120, which adds up to 448. N is 4, so the sample mean is 448 over 4, which is 112. That's the mean IQ of our 4 lecturers. Remember, the test statistic is MS minus MP over the standard error of the mean. So we have the sample mean MS is 112, we just calculated that. We're given that the population mean is 100 and the population standard deviation is 16. But we need to work out the standard error of the mean, which is the population standard deviation divided by root n. Well, the population standard deviation is 16, n is 4, so that's 16 over root 4, 16 over 2, which is 8. So u is 112 minus 100 over 8, which comes to 1.5. So we have a u of 1.5. We look that up in the normal distribution. Remember, we're tabulating the values of the probability p of obtaining a value of u equal to or greater than that shown. And we want a significance level of 0.05, which means that for a one-tailed test, as we've already seen in a previous example, we need u greater than 1.7 to reach significance at the 5% level. Our u was only 1.5, so it has a probability of 0.06, which hasn't fallen below 0.04. In other words, our u value of 1.5 hasn't exceeded the critical value of 1.7. So we conclude that from the table of the standardized normal distribution, for our significance level of alpha is 0.05 and a one-tailed test, we have a critical value of u of 1.7, but we've only achieved a u of 1.5. It hasn't reached the critical value. We don't therefore have a significant result. So we can't reject the null hypothesis. That doesn't mean to say that lecturers don't have above average IQ. It just means that there is not sufficient evidence to support the hypothesis that lecturers have above average IQ. They might well have above average IQ, we just don't have sufficient data here to demonstrate it. So that concludes the third part of this lecture. on comparing means.